Good morning, everyone, and welcome back to the litmus test. Last time we asked the question, how much heat does it take to raise an ingot from room temperature to the melting point? How much heat does it take just to get it hot enough where it can start melting? Today we're almost done in answering our big question, how much energy is in a piece of charcoal. We just have to figure out how much energy it takes to convince a very hot ingot at the melting point to actually melt. It turns out that this takes a little bit of extra energy. Once you get the ingot, or any material, once you get a material, a solid material that does melt, hot enough to melt, it takes a little bit of extra energy to convince the atoms to stop being in their crystal structure. Remember those from a while ago? Once we can convince the atoms to stop being in a crystal structure and break all of those bonds between them, then we can get a liquid. And that's the amount of energy we need to melt a material. That's the other 5 seconds of melting time in the furnace, if you prefer. This is going to be a lot more straightforward than the last video was. So, looking at our roadmap, we're going to look at the last 2 lines today, and we're going to start with N, the number of moles. We figured that out last time. And HF, which is just the heat of fusion, how much heat it takes to melt something. And we're going to get another value here, the change in enthalpy, and then just another value of heat. And then we can use the value of heat here and the one from last week to get the total value of heat needed to actually melt the metal from room temperature. So let's start here. That's really, not too hard. Let's put a sign down. We know from last time that we had this many moles. Did I get it wrong? Oh, it was 2,4. My bad. I also have a small confession to make, a small correction to last week's video. I messed up this orders of magnitude. They were supposed to be e to the 8 and e to the 5, not e to the 9 and e to the 4, or 6. So this is how many moles we have, and we're going to use a very straightforward formula here, where we're going to say that we'll just use Q. The heat in this case is just equal to the heat of fusion times the number of moles. And then all we need is to know what a heat of fusion is, and conveniently that's in our thermochemistry book. If we look over here, heats of fusion. Now notice that the heats of fusion are listed in kilojoules per mole. So the answer that we get here is going to be an answer in kilojoules. However, this is done to keep these numbers in nice normal range of numbers, just like our specific heats, which were in joules, are in the orders of 20s. Now our heats of fusion are on the orders of 13, except for a couple. Lead down at 4, osmium way up at 31, and over here at steel, steel's a little bit different because steel doesn't care about molar mass. Steel just cares about raw mass. Steel is in 250 joules per gram, but in kilojoules that's 0.25, so that's relatively small as well. Steel's pretty easy to convince to melt once you get there. Keep in mind, though, that that's per gram, not per mole, so that's not an exact comparison. Really, steel is probably very similar to iron and nickel in its heat of fusion. So let's run this for copper real quick, because that's what we were using last time. That's where we got this number of moles from. And our heat of fusion for copper is 13.26 kilojoules per mole, so 13.26. So that's going to give us a total heat of, calculators out everyone, that's your 15,663.24. We're just going to multiply that by the 13.26, and we're going to get this big number, 207,694.56 kilojoules. So this is a number on the same order as the number over here to the right. The number over here to the right was 407,000 kilojoules, and this is 207,000 kilojoules. We can make this a little bit easier to read by getting rid of all this other stuff and saying 2.08 times 10 to the 5th kilojoules. 208,000 kilojoules. So we have 208,000 kilojoules. That's about half the amount we needed to get it to melt. So to get it to get hot enough, was it 400,000 to convince it to melt? just another 200,000. Not very much at all. So already you can see where this is going. All we're going to do is we're just going to add up these two heats, and we should get a final heat. So the total heat, which I'm going to call delta H, or enthalpy, is just going to be Q1 plus Q2. In other words, this is the amount of heat it took to get hot and the amount of heat it takes to melt. Okay? We can write that in words. Heat equals hot plus melt. Total heat, how much to make it hot versus how much to melt. All right, well, that's pretty straightforward. 2.08 e to the fifth plus 4.07 e to the fifth. Without any other significant figures, we can add that up, and we'll get, well, 8 plus 7 is 15, so 6.15 e to the fifth kilojoules. Now, those e to the 5s don't actually add, because this is really, 200,000 plus 400,000. For a more accurate number, or I should say for a more precise number, this is what you would get if you didn't do all that rounding. 615,338.1 kilojoules, which conveniently equals, in fact, we just say this is just the same as 338 megajoules. 615 megajoules, 615 million joules of energy are needed to convince copper to go from room temperature to hot, to the melting point, and then to convince it to melt, to actually melt. So that means that a piece of charcoal has at least that much. In fact, a piece of charcoal should have 8 times that much of stuff, right? Because a piece of charcoal can melt 8 pieces of ingots. All that weather, a piece of charcoal can melt 8 ingots, right? So charcoal actually contains 8 times that, at least, right? And so if we do that real quick, and we put H times 6.15338, we end up that charcoal has a whopping 4922.7 megajoules, which is another way of saying 4.92 gigajoules in a piece of charcoal. 4.92 gigajoules in charcoal, and that's just for copper. If you did any of the homework from last week, you should have noticed something pretty, well, you should have noticed what our most hardest to melt thing was. That was a bad sentence. What is our hardest thing to melt? And it doesn't take much thinking to realize that, well, the hardest thing to melt, there's a lot of multiplication here, right? This requires, this big C, this big delta T. So something that has a lot of specific heat, something that has a very high melting point, and that N, of course, is bigger, something is more dense. Well, what's our densest item on here? Osmium. Specific heat. What has the highest specific heat? Well, they're all pretty similar, but the highest is actually here in uranium. Well, what's the highest heat of fusion? Well, we'll come back to that. What's the highest melting point? Osmium is much higher melting point than uranium. Much higher. So when you do this math, you notice that osmium is also more dense than uranium. This specific heat difference isn't nearly as big as the difference in the melting point. It should be pretty obvious that the thing that's going to be hardest to heat up should be the osmium. And the thing that's going to be hardest to melt, well, the heat of fusion, again, that osmium at 31, way outclasses anything else here. And its density is going to be really high, where'd it go? There's its density. Its molar mass, here's its molar mass, it's not actually as high as uranium. So osmium and uranium, they could give each other a run for their money. But it turns out that indeed osmium is the highest, with the total heat needed once you go all the way over here, well, over here, once you go all the way over here to this value, that osmium comes out at well over 1,000 megajoules, over 1 gigajoule of total heat needed to melt. Let's put that on a sign too. Say osmium will have a total heat of 1390.9 megajoules to melt. In second place, again, if you've done all your math, then you'll notice that in second place is nickel at about 925 megajoules. Third place is iron at 813 megajoules. And our fourth place winner is actually steel at about 790 megajoules. Sorry, I have to look at all my numbers and I'm getting them all mixed up. So this is how our things rank. Therefore, we know that one piece of charcoal has 8 ingots worth of melting in it, right? It can melt 8 osmiums just as it can melt 8 of anything else. In fact, we can put this osmium in here, and assuming all of the recipes are working properly, right? One piece of charcoal will go through and see it just melts the osmium in the same amount of time it took to melt the copper. So therefore, it must have this as much energy as it needs to melt this osmium. So that's a lot of energy. In fact, here we can just say, well, never mind that, that's 1390. 8 times 1390, what's that? Well, that comes out to 8 times, you've all got your calculators out too, right? It's not just me. Not just me here. Am I doing all the work this time? I get the feeling I am. 11,127.2 megajoules, or in other words, 11,000.1 gigajoules in a piece of charcoal. 11,000.1 gigajoules in a single piece of charcoal, also in a single piece of coal. That seems a little unrealistic. Consider the following. Go home, get a piece of charcoal, get even a bag of charcoal. Go grill. Get a bag of charcoal, go have a grill, get some hamburgers, some hot dogs, some steak, chicken, whatever you like. Go out to the back, light up your grill, get it nice and hot, and see if the grill bars melt. Like, they don't, right? Otherwise, grills don't work. In real life, yes, we do burn coal. And yes, we can generate as much energy as we need to do this. But first of all, we can't actually smelt osmium. It just is way too hard. We can't actually get fire to be, that hot. If we need to smelt osmium in real life, we generally use specially generated arc welding techniques that generate just massive arcs of electricity to melt it. Melting down nickel, iron, and steel, we can do that relatively easily because their melting points are much more reasonable than osmium's, only being like 1800 Kelvin. But we can still do that relatively easily, and we can actually use coal or even hydroelectric power for those purposes. In fact, that's why a lot of steel mills were built in locations that had cheap power near them. We can also do that with aluminum, etc. So we can get that with coal and charcoal, but not with a little piece that we see here in Minecraft, generally. There. I can't actually find my inventory. This little piece of charcoal probably, in real life, a charcoal of this size wouldn't really have enough energy. However, and here's where you got to think. This piece of charcoal basically is an entire cubic meter of wood. And we know that our character can carry ridiculous amounts of weight, like 452 pounds per ingot. Even more for the heaviest. Osmium, think about how heavy these osmium ingots are, being as dense as they are, right? That's just an insane amount of weight that our character can carry on them. In fact, we could fill up our entire inventory here with just 64 blocks of osmium. So it's not unreasonable to think that this piece of charcoal is a little bit bigger than the pieces you would use to grill. Probably a lot bigger. This piece of charcoal is probably at least 1 cubic meter in size. Does that contain enough heat to melt osmium? No. Maybe some of these smaller metals like lead, sure. Tin, yeah, maybe even aluminum. Maybe some iron, I don't know. That's a lot. And the way the furnace is designed, it's tricky to get. But Minecraft charcoal is some amazing stuff. If we could figure out how to make that. At any rate, so that ends our thermochemistry series. You can go home, you can work out some of these numbers yourself. You can go back and screenshot through our thermochemistry book, looking at all of the specific heats, heats of fusion, and all of the other conveniently nice labeled things. Do this for steel. That could be rather interesting because the numbers are a little bit different. Find out for yourself, explore different metals, explore metals that aren't found in Minecraft, and if you happen to be good at coding, maybe you have a way to improve this strange melting paradigm. Why should charcoal actually be able to smelt both osmium and tin? Should we actually consider different amounts of time for smelting? Should we break these two heats apart, the heat for heating something up and the heat for melting? If you're a mod maker, you can consider it. But until now, I hope that this has answered an interesting question for Minecraft. 11.1 gigajoules per little thing of charcoal. That's incredible. And I hope that when you come up to thermochemistry in your chemistry classes, you can look back at this and go, oh, okay, that's the number I need. All right, so until next time, thanks for watching, stay safe, and don't catch on fire.